Dear student, welcome to my channel. Topic of this video is logistic regression, and this is the first part of video. In this video, introduction and the sigmoid function for logistic regression is explained. Now let us start. Logistic regression is a statistical method which is primarily used for binary classification, where goal is to predict categorical outcomes like yes or no based on the input features. Unlike linear regression, which predicts continuous values, logistic regression outputs a probability between 0 and 1. The core concept behind logistic regression is to use sigmoid function to transform linear combination of feature into probabilities. This allows the model to handle binary classification tasks effectively by mapping any input to probability range, typically with a threshold of 0.5 to determine the class level. Advantage of logistic regression include simplicity, interpretability, and efficiency on linear separable data. Examples of binary output. So for such type of examples, we can go for logistic regression. For example, bank may sanction loan or not, individual transaction is fraudulent or not, determine the admittance into school. So in all problems, the binary classification is there. So here in such situation, we can go for logistic regression. Using linear regression for a classification problem generally leads to poor result because of the following reason. Unbounded prediction. Linear regression outputs continuous values that can go beyond 0 and 1, making them unsuitable for probability based classification, and we can't simply claim the value. That is, for example, if answer is greater than 1, make it to 1, and when answer is less than 0, make it to 0. Lack of decision boundary. Linear regression finds the best fit line for predicting values, but it does not create a clear boundary to separate the classes effectively, because still the name is logistic regression, but basically it is a classification boundary, so boundary should be there, but linear regression finds a straight line, so as specific boundary is not there to separate the classes. Sensitivity to outliers. Since linear regression minimizes the square errors, outliers are disproportionately influence the fit, making it even less reliable for classification. So it hampers the linear regression, but if outliers are present in the data and if we go for binary classification using linear model, then at that time the result is more poor. See, this is the output for linear regression and logistic regression. Linear regression simply put the line. So here whatever this side will come to one class and this side will come to another class, but actually the separation is like this. This is one class and this is another class. So this line does not make properly separate classification of this data of both classes, but instead of this line we are going for such type of function, so which will classify the samples between the two classes. So this function, that is S-shape function, is called the sigmoid function. Linear regression, it shows a straight line which can produce output beyond the range of 0 and 1 and making it unsuitable for classification. Even we can see that range, it is going beyond the 0 and 1. Logistic regression shows S-shaped curve which restricts the output between 0 and 1 and making it ideal for binary classification task. Now we will see a simple example of employee promotion. We have data on 1000 employees from a company and we want to understand what influence their chances of promotion. Promotion indicates whether an employee received promotion or not. Experience, by examining how many years of experience affects the likelihood of promotion. So this is a dependent variable and this is an independent variable. Our dependent variable is a binary because either get promotion or not promotion. So it increases from 0 to 1 if an employee is promoted. Therefore, any factor that raises this value boosts the likelihood of promotion. So our equation in the linear model is promotion is equal to beta 0 plus beta 1 experience. So once we find out the parameter, the error is minimized, so error is not here, it is by mistake. So promotion is equal to beta 0 plus beta 1 experience. This is our linear equation. So probability should be bounded between 0 to 1 for logistic regression. So suppose we have range of experience from 1 to 45. Then if we take the linear model directly for this problem, so we can see that some values are between 0 to 1, some values are below 0, and some values are above 1. So for 28 we are getting the value 0.092, so which is okay because it is between 0 to 1. But for 5 it is giving less than 0, and for 35 it is giving more than 1, so which is not suitable for our binary classification problem. But instead of linear, if we use the sigmoid function, then at that time we can see that for 28 it is giving 0.52, for 35 it is giving 0.76, and for 5 it is giving 0.20. So even we can see here that the range is also properly calibrated. So this is the problem. That's why we can't use linear model for the logistic regression, but we are going for the sigmoid function. So here this is a comparison between the logistic and regression. So logistic always lie between 0 to 1, and here it is not bounded. We need to somehow constant p such that that value is between 0 to 1. Here p is a function, that is p stands for probability here, that is answer is between 0 to 1. So it is a function of experience, but the linear function didn't work. So we already seen in previous slides that this linear function will not work. So we have to find out the function which satisfies the two things. First, it must be always positive, and that is p is greater than or equal to 0, or in fact it is p greater than 0, and it must be less than 1. So p should be less than 1. So it should work between 0 to 1. So why not exactly equal to 0 and why not exactly equal to 1? Because that sigmoid function will never touches to the particular axis. So I will explain with the example. So our first is that it must be always positive. So when we want to take the positive value, the best is the exponent, that is the e. And here for e function the values are always positive. So for example, see, this is the curve. So here on the positive side there is no limit, so it is greater than 1. But on the negative side we can check that this is coming parallel to x-axis, but it never touches to the x-axis. So as if you expand this diagram, so we can see that this is very close parallel to the x-axis as it is going to the negative side, but it never touches, so its value is not 0. Exponential function has a graph that gets very close to the x-axis as the graph extends to the left, but never really touches the x-axis. So that's why we for this condition that it must be always positive, we are using the exponential, that is if e, and that is nothing but e raised to beta 0 plus beta 1 experience. Our second condition is it must be less than 1. So here it satisfies one condition, that is it is not negative, but here it is can be greater than 1. So for that we are using this factor. So whatever this equation, this is the basic equation, that is e raised to beta 0 plus beta 1 experience. So we are dividing by this factor. So when we divide by this factor, the equation becomes less than 1. So this restrict between 0 to 1. So if we arrange this, we can get this term. So this is our final equation. So this is the equation. This is for between not less than 0, and this is dividing factor, so that it will lie between 0 to 1 or not greater than 1. So this is the final equation, but we can easily convert this equation into this format by dividing by the term e raised to beta 0 plus beta 1 experience. So this is our final equation, that is sigmoid equation, that is S-shape equation for the logistic regression. So the here parameters that same we are using in linear, but here we are not straightforwardly using the linear function, but we are using the non-linear function, and which is of the format p equal to 1 plus e raised to minus beta 0 plus beta 1 x or any one of the feature present in the table. So this function, that is whatever this derivation derived function, that is this function, is called the sigmoid function. The sigmoid function is crucial in logistic regression. It is used to map any real valued number into the range between 0 to 1. This makes it ideal for binary classification task where the output represents a probability. The sigmoid function, it is represented by sigma z 1 divided by 1 plus e raised to minus z. So here z is nothing but beta 0 plus beta 1 experience, where z is equal to beta 0 plus beta 1 x for a single feature, and if multiple features are there then it gets added. Beta 0 is the intercept and beta 1 is the coefficient for the feature x, and here feature is nothing but experience. As z approaches positive infinity, sigmoid function approaches to 1, and when z approaches to negative infinity, it approaches to 0. So the S shape ensures that probability output never exceeds between the range 0 to 1, which suits for binary classification like yes or no. And the main advantage of sigmoid function is that sigmoid function is differentiable, which is helpful to optimize through gradient descent in training the logistic regression model. So this is sigmoid function. It is represented by like this: sigma of z equal to 1 upon 1 plus e raised to minus z, and here instead of z we are using our linear function, which is beta 0 plus beta 1 x or experience, and this function gives the guarantee that it will lie between 0 to 1. So here it really when it is going to the positive infinity, it is not 1, it is going very parallel to this axis, but it never touches, and same for here. So when we are using the exponential function, at that time for all these experience values we getting all the value between 0 to 1, and they are very much properly calibrated. Now here this is the p, this is nothing but the probability. So p and 1 minus p is simply represented as, and if we take the p divided by 1 minus p, so log of odds, that is p divided by 1 minus p, is called log of odds or logit. So log of p divided by 1 minus p, we get simply beta 0 plus beta 1 x, and if we remove the log, then we will get e raised to beta 0 plus beta 1 x. So as this is nothing but the odds of log, so that's what is called also logit function. Now this is basically sigmoid function. So now when e raised to this term, that is when e raised to beta 0 plus beta 1 x depends on this value, so this is z. So when this value is 1, so equation becomes 0.5, not 0.52, 0.5. When this value, that is z, when this z is 0.5, sorry, so z is 0, this is 0. So when z is 0, that is 1 upon 1 plus e raised to 0. E raised to 0 is 1, so 1 divided by 1 plus 2 is 0.5, so it becomes 0.5. When z becomes positive infinity, at that time it becomes 1, and when z is minus negative infinity, it becomes 0. So it is bounded between 0 to 1. In logistic regression, y cap is a non-linear function because in the derivation we require to find out, or we require to reduce the error between the actual value and predicted value. So actual value is either 0 or 1 in a table. So in logistic regression we are using the y cap, that is nothing but predicted value, and for that we are not using linear but we are using non-linear function, which is nothing but 1 divided by 1 plus e raised to minus z. But if we use this non-linear function, then at that time we are not getting the convex shape like linear regression, but various many many local minimas are present. So chances are there, if we use the same algorithm, that to stuck up into the local minima. So that's why we are changing the shape of this function. So that is called log loss or the maximum likelihood estimation. So y is your actual value and y cap is predicted value, but we are not using same as linear regression, but here we are changing basic equation. So in order to solve this problem, we derive a different cost function for logistic regression called log loss, which is also derived from the maximum likelihood method. So that function is total number of records are n, so this is 1 by n, small n, summation 1 to n minus yi into log of y hat, so this is actual and this is predicted, plus 1 minus yi into log of 1 minus yi. So this function is used for the loss function for the gradient descent derivation. So this is all about the function of logistic regression. So in the next video I am going to explain how to derive the logistic regression equation using the gradient descent approach. Thank you.